go with Unit 3. It's our third and final unit with trigonometry. And section 3.1 is called the Law of Sines. We start with a recall. Recall that if we are asked to find missing measurements in a triangle, we have certain methods that we can use as long as the triangle is a what kind of triangle. So we've learned how to use trigonometry in our first couple of units, mainly our first unit. That if an angle was unknown or a side was unknown or something, we could use trigonometry to figure out what that missing side was or that missing angle, as long as the triangle was a right triangle. So basically, the significance of what we're doing in 3.1 here is we're going to start to learn how to solve all kinds of triangles. And so a quick little definition, this isn't going to be the most important vocabulary word in the world, but oblique triangle is technically a triangle that does not contain a 90-degree angle. So again, we are basically going to be learning how to figure out missing measurements, missing angles, missing sides, or unknown sides, unknown angles in a triangle that is not a right triangle. And this section, it boils down to a formula. So the law of sines is essentially a formula. And if the triangle you're dealing with can be labeled like so, if you think of it labeled like so, where the angles are represented by the capital letters, angle A, angle B, angle C, and the sides are represented by lowercase letters, and side A is across from angle A on purpose. Side B is across from angle B, again on purpose, obviously. And side C is across from angle C. And with a triangle like that, you would have, this formula, which, you're never going to use that entire thing. You're going to pick and choose. Like you'll have these two fractions equal to each other, or you could have these two fractions equal to each other, or you could have this fraction equal to that fraction, whatever you needed in the moment, like whatever the moment called for. And so this formula is essentially what's the word that starts with P? When two fractions are equal to each other, that can be called a proportion. So for example, we could say side A over the sine of A equals side B over the sine of B. And of course, it would be like angle A and angle B. So, here we go. Here's an example that says, solve triangle ABC if angle A is 64 degrees, angle C is 82 degrees, and side C is 14 centimeters. Now, when it says solve the triangle, it means, it's not asking for anything in particular. It's not like it's necessarily asking for the missing angle or whatever missing side. It's just saying solve the triangle, and what that means is find everything else. Find all of the missing sides that are not known and all of the missing angles. In this case, there's just one missing angle, which we'll get to in a minute, but I just want to say real quick, like pretty much just once, that you don't need to draw the triangle. I don't know if that was actually in your head, but very often drawing a picture helps you understand it, helps you wrap your brain around it, and come up with the solution and how you're going to do it. But I've never seen any benefit in these problems like drawing the triangle. I don't think it's necessary at all. So here we go. We're going to obviously use the law of sines, but do we need the law of sines to figure out the third angle? We know the first angle, angle A, is 64 degrees. We know angle C is 82 degrees. How do you find the third angle if you know two of them? Isn't that just like real basic geometry, like probably from like middle school geometry class? Because don't forget, I mean, it may have been a while, I don't know. But you probably remember, at least kind of remember, that there's a total of 180 degrees in a triangle. So if there's 180 degrees total, you can just pretty much subtract 64 and 82 from the 180 and get 34 degrees. So angle B must be 34 degrees. And now we can pretty much go after the two missing sides, angle A, or sorry, side A and side B. And to do that, we're going to see how the law of sines comes into play and how the law of sines can be useful. So seeing as how I know that side C is 14, and I know angle C, and I know angle A, so it's like, look, I know this, I know this, I know this. In a proportion, if you know like 3 of the 4, then you can find that missing one. So this is a pretty good proportion to do. I guess we also could have, let's see here. I mean, we also could have started with side B. Like instead of finding side A, we could have found side B, right? But I think we would have had to use this, since side C is the only side we know. I think this fraction was very much necessary to have in our first proportion here. And I guess you could have picked whether to do A over sine of A or B over sine of B as the other fraction. So anyway, plugging in the stuff we know, we get to here. Plugging in the stuff we know. And obviously, we knew already that we didn't know that. We're going to solve for that. Like, that's what we intend on figuring out. And maybe you hopefully may remember how to solve a proportion. Like, what would you do now in order to solve for A? And again, I keep repeating that it's a proportion. How do you basically, what's the cookie cutter way to solve a proportion? Do you remember the whole idea of cross multiplying? Little like gimmick method of cross multiplying where you multiply diagonally and set those equal to each other. So when I cross multiply, when I do A times the sine of 82 degrees, I get this side, and then you write the equal sign, and then you do these two. So the best way to write that is not the sine of 64 times 14, but 14 times the sine of 64. And what do you think the next thing you should do is to solve for A? Well, that would be dividing both sides by the sine of 82. And something I want to definitely mention, yes, that's a trash can. Anyway, something that I want to mention pretty much around this time is you might have thought about writing what this is from your calculator and writing what that is from your calculator, or maybe at this point in purple now doing it like, what is the sine of 82? Some decimal that I'm going to have to round. What's the sine of 64 degrees? You might have thought about doing that. But again, that's a decimal you have to round. So what I'm getting at here is, don't. Try to be as exact as possible. And at the end of the day, you're going to have to approximate. You're going to have to do 14 times this divided by that. But I would try your best to hold off until the way end to actually do any rounding. Because if you round this and you round this like along the way, like you round that, and then you do math with the two rounded numbers, then your final answer can be like a little bit more off than it easily should be, or could be anyway. So yeah, anyway, so again, try to wait until the way end when you do this math, and you could throw all this into your calculator at once. And so your bestest answer rounded to the nearest three places is 12.707 centimeters. And then the rest of this problem, I don't think I need to drag our way through this one so slowly. Now we're just going to, do the same thing, but finding side B, right? And I would definitely use this fraction again. I wouldn't use the B's fraction and the A's fraction, because if you're going to use the A's fraction, half of that A's fraction is using a rounded number, and so, little c was exact, so use the C's fraction again. And again, plug in what you know. You cross multiply, and you get to here, and then you divide in order to get the B by itself, and you get that. And so that's how we use, well, that's our first example of using the law of sines. Our next example is similar, because looks like we have 2 out of our 3 angles, right? And if we have 2 out of our 3 angles, just find the third angle by using, very simple middle school geometry, by figuring out like how many of the total 180 degrees do we have left for the third angle. So it looks like angle B is 117.5 degrees. And next we would need to find, let's see, so we would need to use, now look, I'm pretty sure there's nothing more for me to teach, I think, as far as this problem goes. So if you want to pause the video and try this one on your own, I recommend you do that and try to finish this on your own. I probably should have told you to try this one even before I revealed what angle B was, because you knew enough to find that too. But I think you could do that, pause the video, and then unpause when you want to see what I do. But so the next thing we would do is find either side A or side C. We're going to have to use that to do it. So we're going to have to use the B over sine of B fraction, right? And I guess we might as well go in alphabetical order, I don't know. And let's go after side A first, because we know little b and big B, and we know big A, angle A. So we can plug in what we know. When a fraction is equal to a fraction, we can do cross multiplying, and we get to there, and then we divide by the sine of 117.5 to finish getting side A all by itself. And we try to hold off on rounding until the way end, and we can do on our calculator, make sure your calculator's in degree mode. Duh. And we do 12 times the sine of 40 degrees, and then divide that by the sine of 117 without rounding anything along the way. And that's what you should have got for side A. And then, use this fraction again to figure out little c. And nothing really additional to teach you, just doing the same thing again. Cross multiplying, and solving for little c. So here we go with this next one. And yes, you might, like, there was nothing new in the last example, but trust me, there's going to be some new stuff here. So here we go. Triangle, ABC, solve it. If we have this as our angle A, big A, that's little a. Okay, so look, we have enough for one fraction, and little b equals 26. Okay, well, here's something new. How many angles do we have given? Just one. So we can't start off the easy way like we were before, but it looks like we do have enough to make a proportion, because we have big A and little a, and we have little b, so I think we're going to be able to find big B. So again, this was little a over the sine of big A equals little b over the sine of b, and we can cross multiply in order to try to solve for big B. So we get here with our cross multiplying, and then what are we going to do? You know, I guess just divide both sides by 33, but that doesn't get angle B by itself. It gets the sine of angle B by itself. So what do we do with this? Because we want to know, we want to know what B is, not the sine of B. So do you remember what we do here, gang, when we have like the final answer? Like, I know this is, you know, not not the cleanest final, but we have the final answer and we need to know the angle. What do? We do the inverse sine. Okay? So angle B will be the inverse sine of this answer. And yeah, like, you could put all that in your calculator at once, no problem. And what your calculator probably says is about 41.359 degrees. But I hope from everything we've done so far in the first 2 units of trigonometry, I hope this isn't like a total shock that this is not the only possible answer for angle B. Like, if you do, you know, if you're solving an equation like this, the sine of what angle will get you whatever that is. There's not just a quadrant 1 answer. Wouldn't there also be a potential quadrant 2 answer? Right? So again, like, there are actually there's an angle in quadrant 1 that could make this true, and there's also an angle in quadrant 2 that could make this true. So if that's the angle in quadrant 1, what would be the other possible angle in quadrant 2? Well, I will draw a picture now. You know, I definitely think a picture could help in this situation. So if you kind of draw, all right, so we have like an answer in quadrant 1, and we have an answer in quadrant 2. If that quadrant 1 answer was 41.359, approximately that degrees, then this angle would also be about 41.359 degrees. Because this angle, this reference angle or whatever, has to match that reference angle. And so if this angle right here is about 41.359 degrees, then what is that angle, that quadrant 2 angle? Like, what's that angle? Wouldn't you do 180 degrees minus that? You know, like, look, 180 degrees minus that reference angle of 41.359 to get the angle of 138.641 degrees. So, I mean, now look. Oops. So, do we have two possible answers? I mean, that might have took you totally off guard in the first place. Wait, two answers? And yeah, so let me kind of, I don't know, maybe I'll kind of go back to these guys. You might have noticed that along with this example, it had this kind of thing, you know? And in a way, we could totally refer to this kind of example as an SAA triangle. Do you remember back in the days of geometry class what SAA stood for and what it meant? Maybe, and what it, well, if you don't, I'll tell you, it's side angle angle. Or actually, you might have seen this as AAS instead. Angle, angle, side. Whatever, same thing. So, in fact, I guess that's probably more likely that you saw it in a textbook or with your teacher as AAS, angle, angle, side. And so do you remember what angle, angle, side was all about? Well, what it was all about was if you knew that two triangles had a matching angle, angle, side sequence, like one of the triangles, angle, angle, side in a row, matched another triangle's angle, angle, side in a row. That's all you needed. You didn't know anything. You didn't need to know anything else matched for sure. That was enough to go ahead and conclude that the two triangles were the exact same two triangles. That they were equal and equivalent in every way, or congruent. Man, I'm good. I think the word in geometry was congruent. I haven't taught geometry in 12 years. But yeah, anyway. So that's what that was all about. So here's the thing. Since angle, angle, side was one of those ways to go ahead and conclude that yes, the two triangles were completely congruent. Well, and here's the thing. Here's what it means here. If what I'm giving you, and that's what this is over here. This was an angle, angle, side, in a row. And if that's what you have, that locks you in to one triangle and one triangle only. Let me say that again. If what you have is angle, angle, side, or side, angle, angle, same thing, that locks you in to only having one potential possible triangle on your hands. And that's why, there's only one answer here for angle B. There's only one answer for little a. And there's only one answer for little b. But here's the thing. Another comment before we get back to what we were doing. I didn't address that, or I didn't address this when we first did this problem. This is not even something you have to take notice of. When I give you a problem on a test, or when you take a quiz, or you're doing your homework, you don't need to pause and say oh wait, is this angle, angle, side, or what is this? You don't even need to notice that. I don't care. I mean, when you went ahead with your formulas, with your law of sines, you only got one answer. It's not like you ever were faced a situation where you could have had another answer, right? And so it just kind of played out the way it did. Guess what? The same with angle, side, angle. The second example we did was actually turned out to be angle, side, angle. Well, if you think back to geometry, that was another situation that would lock you in to only being one possible triangle. So yes, since this turned out to be angle, side, angle, there was only one possible answer we could have got. And that's just the way it happened. When you solve for little a, that's what you get. When you figured out angle B, that's what you got. But here, okay, yes, I mean, what really matters, like what really tells the tale about getting a second possible answer, is that you ended up with this scenario. Well, really this scenario, I guess, I'll include both these steps. When you have like the sign of something equals an answer and you want to figure out the angle, there's going to be, well, remember from like last unit, technically there's an infinite number of answers, but you kind of start with, in this case, the quadrant 1 answer and the quadrant 2 answer, right? So when you end up doing like an inverse sign, it's not so much that SSA was not one of those geometry situations. It's just that when you do inverse sign, that's two possible answers in the first time, between 0 and 360, right? There's two possible answers. Okay? Now, here we go. Could angle B be 41.359 degrees? Yeah, that would make sense. But would this angle make sense? Could our angle B instead be 138.641 degrees approximately? No. Okay? It turns out that it's actually not. And why? Well, if your first angle, if angle A is already locked in as being 57 degrees, how can your second angle be that big? There's not enough degrees left over. Remember, there's only 180 degrees total in every triangle. So it's not even possible. So yes, in a vacuum, there's two, and there's actually an infinite number of solutions to this equation. But considering the context here, we're actually trying to solve measurements of an actual triangle. There really is only one solution. So we call this the ambiguous case, SSA, because this does not lock you in to one and only one answer. I know here there was one answer, but there's still more examples to go. But anyway, so the rest of this, we can now find angle C. Like now that we have a second angle, we can find our third angle, like so. And we can find the third and final side C. Now that we know that angle C is approximately that. And look, I know like it makes me cringe a little bit that we're using an approximated angle C to figure out little c, but I don't know. I mean, you got it. I'm not going to be that, strict about being super exact. This works 38.930 approximately for little c. So that's, hey, but again, sorry to be a broken record, but you don't really need to look at this and go, wait a minute, that's SSA. This is the ambiguous case. All you have to do is go through the motions of, hey, what I have is big A, and little b. I can find big B by using this proportion, but when I actually execute all these steps, I end up doing the inverse sign. This is what I would recommend is like your red flag. Not so much drawing the picture and going, hey, this is SSA. No. If you get to a point in your solving where you end up having to do like an inverse sign, that's where you take notice and you go like, oh man, I have to consider not just the quadrant 1 angle answer, but also the quadrant 2 angle answer. And in this case, this one was unrealistic. Let's see what happens here. This is going to be, again, the ambiguous case SSA. So again, it's big A, and little b. So we're going to utilize the same law of sines, proportion, and the only thing we can really go out to find here is big B, right? Plug in what you know, as we've been doing. Cross multiply. And we can only really get the sine of b by itself by dividing both sides by 10. And so now we get to here. And see, we get sine of b by itself, and then we do the inverse sine in order to figure out angle b. And we're going to be ready to not just have a potential quadrant 1 angle, but also a potential quadrant 2 angle. So I want you to try this on your calculator. Pause the video and try to do the inverse sine of this entire fraction in parentheses, and then unpause when you're done. Well, what you should have got was some kind of error. And if you're wondering why or what you did wrong, you didn't do anything wrong. Here's the thing. There is no solution here. So yes, it is possible that if you are presented with this would be your angle A, that would be your side A, and that would be your side B, guess what? Those measurements would not form a triangle. It would be impossible to actually draw a triangle, construct a triangle, if those had to be those three measurements for angle A, or side A and side B. It's just impossible. And so there is no answer here. Again, side-side angle was not a thing in geometry. That doesn't lock you into a triangle. It doesn't have to mean anything. Okay? So we have, this was a one solution situation, and guess what? There's also a no solution situation. Let's see what happens here. Once again, we have big A, and little b, and that means that's the go-to proportion where we plug in and we're going after angle B by cross-multiplying and then getting the sine of B by itself and then doing the inverse sine in order to figure out what angle B is. So go to your calculator, pause the video, and please figure out what the inverse sine of this entire fraction is, and then unpause. And so your calculator probably told you about, oh, and then you're rounding this off, 49.886 degrees. But you have to train yourself to remember and just, like, this should be, burned into your brain, I hope, that there's going to be, again, technically, an infinite number of answers, but we're only going to really care about, might as well use the same color as before. We only care about maybe like on the first time, like in between 0 and 360, that there was a quadrant 1 answer between 0 and 90, and there's a quadrant 2 answer between 90 and 180. And remember, if that angle is the 49.886, then that angle is the 49.886. And so in order to figure out what the quadrant 2 angle is, we do 180 minus this to get the other possible answer of 130.114 degrees. Okay? Now, obviously, this angle is possible, considering that our first angle, our angle A, is locked in at 35 degrees, then yeah, this quadrant 1 angle could totally be our angle B. But guess what? So could that instead, right? Because if our first angle is 35, and if we choose our second angle as 130.114 degrees, there's degrees left over for an angle C. So guess what? These are both good. These are both good. You know, again, I remind you that this side-side angle situation does not lock you in to one and only one answer. You know, in the one example, we got one answer. In the example we just did, we got no answers. But here's the thing. If I gave you the task, right, of, hey, I want you to draw a triangle. Okay, everyone, draw me a triangle that has that as your angle A, this as your side A, and this as your side B. I'm telling you right now that it is possible to draw two different triangles. There are two different ways to draw that triangle, or finish off that triangle. Just telling you. So here's what we have to do. We have to figure out two completely different solutions, right? Where it's almost like two different dimensions or two different universes, where in one universe we picked this as our angle B, and in the other universe we picked that as our angle B, and we go off like two different forks in the road, or there's a fork in the road, and here's one path you could go, and here's the other path you could take, So I know you're not going to like it, but here's solution one, where we, go with this and continue, and we're also going to have to do solution number two, where we choose instead to go with that angle B. Double the work. So, of course, the next thing we would do is find angle C. And the last thing we would have to do is find little c. At least the good news is there's nothing new left to teach about this. You can just go through the steps to figure out little c. And so this, and this comprise, one of your solutions. But then you have to do like the same thing again. And then you have, or this, and this together would make your other possible solution, your other possible triangle. Okay? And, a lot to take in there, but that is the law of sines.